Chapter 5 Chemical Kinetics. This is the subtopic in chemical kinetics. This is the lesson outcomes. Chemical kinetics or reaction kinetics, the study of the rate of chemical reactions. Kinetics, study of factors that govern how rapidly reactions occur and how reactants change into products. Rate of reaction, speed with which reaction occurs, how quickly reactants disappear and products form. This is the rate of reaction, change in concentration per unit time. So this is the reaction rate per unit time, always with respect to a given reactant or product. If the concentration of reactants decrease with time and the concentration of product increase with time, because the product increase and the reactant decrease. Rate of reaction with respect to given species X. We look at this, rate X. This is the change in concentration per unit time. Look at this. This is the change of concentration, in bracket concentration, divided by the time, change in time, and the concentration in m, molar units, time in second, and this is the unit on rate. And this is the example. Rate of reaction always positive whether the concentration of X is increasing or decreasing. Reactants consume, so the change of the concentration is negative. Need minus sign to make rate positive. So here is a negative, and this is the concentration of reactant, change concentration of reactant divided by time, change in time, and products produced as reaction goes along, so the change concentration of X here is positive, thus rate already positive, so this is actually always positive. This is the rates and coefficients, relative rates at which reactants are consumed and products are formed. Related by coefficients in balanced chemical equation, no rate with respect to one product or reactant can use equation to determine rates with respect to all other products and reactants. So this is the chemical equation. For propane, react with the oxygen. So this is the combustion, and the product is carbon dioxide and water. So rate of reaction, and we look at this is the reactant minus here, and this is the also the reactant, and the product is the positive, and also here is the positive. Okay, look at the coefficient, 1/5, so this one 1/1, 1/5, this is a 1/3, and this is a 1/4. For the product is a positive, and this is for the reactant is the negative. And rates of coefficient, and this is the O2, propane react with the oxygen. Oxygen reacts 5 times as fast as propane, and carbon dioxide forms 3 times faster than propane consumed, and water forms 4/5 as fast as O2, oxygen, consumed. So here y become a negative 4/5 because look at the water, 1/4, 1/4, and O2 is the oxygen, is the reactant, negative 1/5. And 4 here go to here for the O2 and become 4/5. Same goes here. And look at the O2 here, it's the 1/5, so 5 go here to the propane and become a negative 5. So O2 reacts 5 times as fast as propane. So when you look at this, which one do I measure doesn't matter, all interrelated, often determined by which one is easily measured. Change of reaction rate with time. Generally, reaction rate change during reaction, not constant, often initially fast when lots of reactant present, slower and slower as reactants are depleted. Why? Rate depends on the concentration of the reactants. Reactants being used up, so the concentration of the reactants are decreasing and therefore the rate decrease. Measuring rates: instantaneous rate, average rate, and initial rate. Instantaneous reaction rates. Instantaneous rate, slope of tangent to curve at some specific time. Initial rate determined at time is equal to the 0. Average rate of reaction, slope of line connecting starting and ending coordinates for specified time frame. Look at the change in products for the concentration and divide by change in time is equal to the rate. And when you look at here is the 600, you minus with the 150 for the second, and for the concentrations, so 0.03 here you minus with the 0.005 and divide by the change of time. Concentration versus time curve for hydrogen iodide decomposition at 508 degrees Celsius. Rate at any time t is equal to the negative slope or tangent line of curve at that point. So this is the rate is equal to the negative slope according to the graph. And this is the table 13.1, the data at 508 degrees Celsius. And we look at this initial rate, average rate between first two data points. For the first two data points, 0.1 and 0.0716. And you find the rate, so you get the answer 5.68 exponential negative 4 molar per second. Rate at 100 second, so we look at this 100 second, so you use this formula and then you get the rate is equal to the 2.4 exponential negative 4 molar per second. So for the rate at 300 second, so look at this one, rate is equal to the tangent of curve at 300 second, so you get the 6.2 exponential and negative 5 molar per second. Chapter 5, Chemical Kinetics, Part 2. Theories about reaction rates. Reaction rate depends on the concentration of reactants and temperature. Collision theory, based on kinetic molecular theory, accounts for both effects on molecular level. Central ideas: greater number of collisions per second is equal to the greater reaction rate. Minimum energy of collision needed. Molecules must collide effectively to react. Collision theory: as the concentration of reactants increase, the number of collisions increase, reaction rate will increase. As temperature increase, molecular speed increase, and the higher proportion of collision with enough force or energy, there are more collisions per second, reaction rate increase. Collision theory: during a reaction, the particles of the reactants must collide with each other for bond breaking and then bond formation to occur to produce product. Bond breaking absorbs heat energy, and the bond formation release heat energy. Those collisions which achieve a minimum activation energy and with the correct orientation will result in a reaction. These collisions are called effective collisions. If the particles collide with less energy than activation energy or with wrong orientation, it will not result in a reaction. It's called ineffective collisions. Effective collisions, those collisions which achieve a minimum activation energy and with the correct orientation will result in a reaction. Activation energy is the minimum energy the reactant particles must have in order to react. Collision theory, the reactant molecules must collide with one another in order for a reaction to occur. Not all collision between reactant molecules result in chemical reaction. The reactant molecules must collide with sufficient energy and the effective fraction of collision has energy greater than activation energy. The molecules must collide in an orientation that can lead to rearrangement of the atoms. Collision theory, rate of reaction proportional to number of effective collisions per second among reactant molecules. Effective collision, one that gives rise to product. So this is the example. Only very small percentage of all collisions lead to net change. So this is the molecular orientation. So when we look at this is the correct orientation. The orientation of this collision permits reaction and produce nitrogen dioxide and chlorine. So this is the orientation of this collision cannot produce a chlorine molecule. Temperature greatly affects rates. Over moderate temperature range, this is the activation energy unchanged. As temperature increases, more molecules have activation energy, so more molecules undergo reaction. Reaction rate increases as temperature increases. Activation energy, molecules must possess certain amount of kinetic energy in order to react. Activation energy, minimum kinetic energy needed for reaction to occur. Get energy from collision with other molecules. If molecules move too slowly, too little kinetic energy, they just bounce off each other. Without this minimum amount, reaction will not occur even when correctly oriented. Transition state theory, used to explain details of reactions. What happens when reactant molecules collide? Potential energy diagram to visualize what actually happens during a collision. Relationship between activation energy and developing total potential energy. Making chemical reactions happen faster. So when you look at the collision theory, state that for a reaction to occur, particles must collide with the correct orientation and with sufficient energy for a reaction to occur. Different factors affect the rate of the reaction by affecting the frequency of particle collisions. And we look at this as the correct orientation and sufficient energy. If wrong orientation and insufficient energy, there are no reaction. Increased concentration of reactants. In solution, increase the rate of reaction as there are a greater number of particles available to react. So this increases the frequency of collisions between particles. So increase the concentration will increase the frequency of collision. Increased temperature of reaction will increase the kinetic energy of particles. This increases the frequency of particle collisions, and a greater proportion of collisions will have the energy required to react. Thus mean increased temperature of fraction will increase frequency of collisions. Increased surface area of reactants increase the number of particles that are exposed and available to react. So it will increase the frequency of collisions. Increased pressure of friction will increase the frequency of collisions. Because the gas particles closer together, so they will increase the frequency particles collision and will increase the rate of friction. Use a catalyst in the reaction. A catalyst provides an alternative route for the reaction with a lower activation energy. This means that particle collisions need less energy in order for reaction to occur and increasing the rate of the reaction.